Greetings. This video demonstrates the separation of a mixture of ethanol and ethyl acetate using Aspen Hysys. This mixture forms a minimum boiling azeotrope, which presents a challenge for separation. But because the azeotropic composition shifts significantly as a function of pressure, we can potentially use a two-column sequence operating at different pressures to affect this separation. Let's look at some of the background information before we jump into the simulation itself. Here you see a set of experimental data for this binary mixture measured at 40 degrees C by the authors you see here. These data were taken from the Dikema compilation. You can see at that temperature, the azeotropic composition is at a mole fraction of about 0.67 in ethyl acetate. And the maximum in pressure, the azeotropic pressure, you can see here is about 220 millimeters of mercury, or about 29 kilopascals. Here is a second set of data measured by the same authors at 70 degrees C. You can see that the azeotropic composition has shifted. Now it's at about a mole fraction of 0.55 ethyl acetate. The corresponding pressure is about 716 millimeters of mercury, or about 96 kilopascals. So if you look at these data, and let's consider that we have a feed of a 50-50 mix of these two components. If we feed that mixture to a column operating at 29 kilopascals, the top stream will be this azeotrope, and the bottom stream will be pure ethanol. Then if we take that azeotrope and feed it to a column operating at 96 kilopascals, that means the feed will be over here. Then the top product again will be the azeotrope, but at this composition, and the bottoms will be pure ethyl acetate. So if we can do this separation, we'll have two product streams, pure ethanol and pure ethyl acetate, and the azeotrope streams will be recycled internally, and so we'll have no off-spec product. So let's see if we can do that. Let's jump into the simulator for a minute and select our components. Ethanol and ethyl acetate. Next thing we need to do is select a fluid package. And we're going to choose the NRTL model for our purposes today. Now, already in Hysys are a set of parameters that were taken from another set of data. And using these parameters would probably give a reasonably good simulation, reasonably accurate. However, we can do a better job if we build in some temperature dependency to the parameters that are in this simulation. And so going back to those sets of data that were taken at 40 and 70 degrees C, we can actually fit those parameters, those activity model parameters, with some temperature dependence. Here's a little sheet that demonstrates how you do that. You can see here the Wilson equation and the NRTL equation. The A12 and A21 parameters that you see in the Dikema compilation, as well as what you see in Aspen Hysys, are the numerators in these two equations for the Wilson model, the difference in the small lambdas, and the difference in the G's, these numerators, for the tau equations for the NRTL model. We can take the parameters from two different temperatures and fit the parameters A12 and A21 to this simple temperature dependence. And then we can put those parameters in the simulator and do a more accurate job of representing the behavior of this binary mixture. So I've taken those parameters from the two data sets that we discussed, 40 and 70 degrees C data. Here are those temperatures in Kelvin. And here are the parameters that you read off of those data pages. A12 and A21 for 40 degrees C, and A12 and A21 for 70 degrees C. The alpha parameter, also important in the NRTL model, has a little bit different value for these two sets of data, and we will assume that an average between them is a sufficiently accurate representation of the data. And then here are those linear models. And so we're going to fit A12 to this dependence using the two A12 values at the two different temperatures, and A21 similarly to the two values at the two temperatures here. And you can see this little plot shows you that fit, that temperature dependence of the two parameters, A12 and A21. That gives us these four constants that we can put into the simulation. So here's A and B and C and D. Pull this off to the side so we can see them. And so we'll replace the parameters that are already in Hysys with these temperature dependent values. So this one will be 4088.65. And the simulator always asks us if we really want to make these changes, and we do. This is the C value, minus 1446.12. And then the B matrix will be the temperature coefficients from our regression. So minus 10.475 and plus 4.888. And we'll put in our slightly adjusted alpha value. Okay, so now we have all the parameters in, and we're ready to proceed with the simulation. A valuable tool that Aspen Hysys has as a little calculation unit. It's a little equilibrium operator. So pull it onto your simulation and let's take a look at it. We can have the simulator plot a set of values derived from the activity model and activity model parameters that we have in there to see if this is an accurate representation of the experimental data that we've looked at from the authors shown in the Dikema compilation. You can see that we've done a pretty good job, and you can look at the azeotropic composition there at about 0.67, and that's what we had. So that's a good indication. We can also look at the 70-degree set and see that the azeotropic composition has shifted to about 0.55. So that's comforting, and it also confirms to us that we have accurately input the parameters. So now let's close this, and we'll take off this equilibrium operator and get to our simulation. So let's first of all put in a feed stream. We'll call it feed. Put it in at about 60 degrees C and pressure of about 120 kilopascals. Let's use a flow rate of 1,000 kilomoles per hour with an equimolar composition. Okay, there we have our feed. Now, before we proceed, we know that we're going to have a recycle stream from the top of the second column that's going to be sent back and combined with the feed stream to be fed to the first column. A valuable tool in the simulator is to use a mixing unit to combine such streams as the recycle and the feed stream. Doesn't mean this is a real piece of equipment. It might just be a T in a pipe, or it might be a small tank, but it helps the simulation do its calculations to include this unit here. So we will put that there, and then let's go ahead and put in a distillation column. Remember, this column is going to be operating at the lower of the two pressures. So then let's put a pump after that first column, and then we'll put in the second column. Decrease the size of this a little bit. Okay, now we can start connecting things and see if we can start making this work. We'll attach our feed stream to the mixer and the stream out of that to our first column. Before we get further, I want to pretty this up just a little bit. Give us a little room here. Okay, let's open the first column and start putting in the information we need to do this simulation. Okay, we need an energy stream for the condenser, and we'll call that Q condenser 1 for the first column. Need a reboiler energy stream, we'll call that Q reboiler 1. I'm going to use a total condenser, and our top product will be top 1. Bottom product we'll call bottom 1. Reboiler looks good. Remember, our pressure for this column is going to be about 29 kilopascals. Not going to worry about pressure drop right now. We can do that refinement later on. And we'll guess at the temperatures. And we'll guess at a liquid flow rate out the top. And we'll guess a reflux ratio of about 2. Okay, so now we've put in the specs we need to try to get this to converge, but there's a few other specs I want to add before we actually try it. One spec that's valuable to keep an eye on is the boil-up ratio. Just like a reflux ratio, but for the bottom of the column, and it's valuable to see how that's performing. We'll add 2 other specs, and these are purity specs for the top and bottom of the column, respectively. The top one we'll call distillate 1 purity. This, of course, will be associated with the condenser. And remember that at the top of the column will be the azeotrope. We thought that would be about a 0.67 mole fraction of ethyl acetate. And we'll add one last spec, another fraction spec to the bottom. Call this bottom 1 purity. That will connect with the reboiler. And remember, we said we should be able to get pure components out of the bottoms of these columns. This first column, we should be able to get pure ethanol out. So let's put in a spec of 99% for ethanol. Okay, now we've got all those specs. Now this liquid rate at the top is probably not a great estimate. So I'm going to instead specify this bottom purity, which I think is a good spec, and deselect the distillate rate. And you can see the column converges immediately. And so we've got a functioning column. The Temperature profile looks reasonable. Our reflux ratio is 2. Our boil-up ratio is about 7.5. Our distillate purity is pretty close to the azeotropic composition that we estimated it to be. And of course, our bottom purity is at the specified purity since that's an active spec. We could even make this a little bit higher purity. Let's try that, 0.995. Okay, so that looks good. Let's proceed on. We'll call that column good enough. Before we do, though, I want to point out one thing. It's a valuable process to specify purities when you're trying to get a simulation to converge. But when you're operating a real column in the real world, you don't operate off of purity spec. You change flow rates by opening and closing valves. And so even though it's valuable to use purity specs to get simulation to work, at the end of the day, when you've got your simulation working, you want to change those purity specs to operational specs like boil-up ratio so that when you actually build this process, you can operate. But for now, we'll leave it on the purity spec because we still have more work to do to get this simulation to converge. Okay, the next thing we want to do is take the top azeotrope and increase its pressure before we go to the second column. Need to provide an energy stream, and then let's simply go to the outlet stream and we'll specify the pressure we want to get to, and let's say it's 120 kilopascals. Okay, the simulation completes the calculation, and we're ready to feed that stream to the second column. Okay, I'm going to move this a little bit just to get things to line up a little better. Okay, let's open that second column and start working on it. Again, we need an energy stream for our condenser, Q condenser 2. And Q reboil 2. Total condenser again. Top 2 for our top product. Bottom 2 for a bottom stream. Boiler's okay. Remember, this column's going to be operating at 96 kilopascals. We'll estimate the temperatures. Again, these are just guesses at this point. Guess for liquid rate, and again, we'll use a 2 for our reflux ratio. Okay, we're all done. Now again, just like on the first column, we want to add 3 more specs. At a boil-up ratio, at a value of 2. The top purity spec with the condenser. And again, we said the top of this higher pressure column will be the azeotrope. That's at about 0.55 mole fraction of ethyl acetate. And finally, we'll add bottom's purity spec. We'll call this bottom 2 purity. Like that to the reboiler. And we should get pretty pure stuff out the bottom here. And this is where our ethyl acetate comes out. Okay, so we have all of those specs. Now let's see what happens. Again, I'm going to deselect the distillate rate and select the bottom purity. And you can see we get pretty quick convergence here. Again, we've got pretty good temperature profile, reflux ratio of 2, boil-up ratio is pretty high, 12.5. We're getting our bottom purity. Let's see if we can sneak that up a little bit more. We did with our first column. Okay, so we got both columns operating at 0.995 purity of our product stream. Okay, that's good. Now, as we've said before, we want to recycle this top azeotrope back, combine it with the feed to the first column. And to do that, you'll want to use the recycle unit that's in Hysys. Now, this is not a piece of equipment. Remember, a simulator is a calculator, and this recycle unit helps the simulator do the cyclic calculations of trying to get a recycle loop to converge. So we'll put that there. We will connect the distillate stream to it. We'll pull a stream out here. Now we're eventually going to connect this to the mixer, combine it with the feed. But one of the challenges with simulation is getting it to converge with a recycle stream that's going to build up in material as it iterates. And oftentimes the simulation has a hard time converging in that situation. So a valuable trick is to add a stream that we'll call a dummy stream, and we'll label it dummy, pilot dummy. And then, oops, get my title in right. That again, okay. And what we're going to do is we're going to make this dummy stream look like this recycle stream. We'll connect it to the mixer, and we'll do that a few times, and that will help the simulator get to a close to converge place before we actually hook up the recycle stream. Okay, so let's take a look at this stream. Temperature of about 70, pressure of 96, and a flow rate of 594. And ethanol composition of 0.41. Okay, so let's do that with this dummy stream. On a temperature of 70, pressure of 96, flow rate of 594. Again, our composition was 0.41, 0.59. Okay, so now we'll attach that dummy stream. You can see the process stays converged, but now let's look at our recycle stream. You can see it's much larger now as we've added that material flow from our dummy stream. This stream is obviously much larger. That our composition's about the same. Okay, so let's just change the flow rate to 1010. Okay. Everything is still converged. That's good. Now it's gone up to 1298. Let's change that value here. Now, prior to doing this simulation, we did the calculations for the material balance so that we know what we expect this stream to be in terms of flow rate, and we're getting pretty close to that value. Now we're at 1500. Let's change this to 1500. Everything stayed converge. Okay, so now let's see if we can make this work. So to do this, put your simulation on hold and then break the connection with the dummy stream. And then attach the recycle stream. Move this a little bit. It's a little better. Just leave the dummy stream there. And then we'll go back and make the simulation active. And hopefully we've done a good job. Everything will converge. We'll have a process that accomplishes what we needed it to do. Let's take a look at our two columns. Make sure they're still looking good. You can see our temperature profile is looking good here for the first column. And our second column, temperature profile, is also looking good. And again, we specified 99.5% pure on both of our product stream. So we have a simulation that's working. We're taking this 50-50 feed of ethanol ethyl acetate, and we're separating that using two columns to two pure streams, pure ethanol and pure ethyl acetate. And so we've accomplished the task. Let me go back in to this column. And as I said before, at the end of the day, we want to change our parameters from purity specs to things that we can actually control. And so you can see the boil-up ratio here is 12.61. So let's change what we specified that to be to that value that it's using right now. And then we can change the spec from the purity spec to that boil-up ratio, and you can see the column stays converged. But now we've got controllable parameters, things that we could actually control if we built this distillation column and we're trying to get this separation. Okay, we can control reflux ratio, we can control boil-up ratio. Okay, so now that column is operating with good specifications. So let's do the same with the second column. Boil-up ratio is 15.48. We use that. And again, everything stays converged. We've still got the purities we want, but now we're operational. Okay, there you have it. Process to separate ethanol and ethyl acetate. And even though we had a minimum boiling azeotrope with two columns, we can accomplish this separation and have pure product streams.